as darkness, and then bang, giving birth to an endless expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. They are humanity's eyes and ears in deep space, exploring the plains of Mars, the geysers of Saturn's moon, and the blazing surfaces of distant stars. They are space probes, robotic explorers that are now humanity's interstellar avatars.
They can go places and see things that we could never do from here on Earth.
Space probes fan out across the solar system, returning data that change everything we thought we knew.
If we could find indigenous life elsewhere in our galaxy, it would be one of the greatest discoveries in the history of humans.
Probes collide head-on into icy comets, photograph the edge of the universe itself, even seek planets in other solar systems.
We're at a golden age in the search and discovery of Earth-like planets.
A new generation of robotic explorers is redefining the galaxy itself by unlocking secrets of the space probes. At this very moment, millions of miles from the Earth, human beings are sampling, measuring, photographing, and even sniffing the dust and gases of other worlds. But not in person.
The environment of space is very hostile to people. It's got extremes of temperature, extremes of vacuum, high radiation fields, all kinds of things that are really inhospitable to human life.
Our eyes and ears are robotic proxies, sent on missions to discover the secrets of our solar system and beyond. They are space probes, and they were built to survive the hostile atmospheres and perilous worlds that mankind cannot.
Our space missions are able to survive these difficult environments, and they can go places and do things that we could never dream of without them.
Some probes, like the Hubble Space Telescope, float comfortably in Earth's orbit, while others, like Deep Impact in 2005, are ordered on kamikaze missions to smash satellite probes into comets. Others are sent to uncover the secrets of planets like Mars, Jupiter, Saturn, or their moons, imaging and analyzing them from orbit and landing on their surfaces to explore or dig for samples.
Our probes are used to answer fundamental questions about planetary composition, atmospheric composition, geologic atmospheric processes, how are planets both similar to and different than Earth, and the big picture question, is there life?
The hunt for life on other worlds began over 2,000 years ago when Greek astronomers began gazing at planets. In the 21st century, humanity is finally poised to find it.
Sending out probes into the solar system and even beyond is part of a long-standing mission we've had to understand not just ourselves here on Earth, but the rest of the solar system. And in some ways, that quest helps us learn more about ourselves in terms of where we may have come from and whether there are any other examples of the environment we see here on Earth.
The latest quest begins with an ultra-high-resolution digital infrared roadmap. On December 14, 2009, a Delta II rocket delivered a small package into orbit 300 miles above the Earth. It's called WISE, and it's creating the most detailed infrared photograph of the universe to date.
WISE is the Wide Field Infrared Survey Explorer, and it's a small-sized telescope about 40 centimeters in diameter, so that would sort of fit under my arm here, and it's surveying the entire sky at 4 infrared wavelengths. Everything from the Earth's closest neighbors, the asteroids and the comets, to the most distant parts of the universe.
Unlike the Hubble telescope that generally images wavelengths of visible to ultraviolet light, WISE probes the universe using infrared light.
Human beings perceive infrared as heat, When we feel the sun's warmth on our skin, what we're really sensing are the infrared rays coming from the sun. I'm pouring out infrared light as I sit here, and we can use infrared to look for things that are sort of similar temperature, like, for example, asteroids. We can also use infrared to look for the most distant galaxies in the entire universe.
Many of these distant galaxies can't be perceived in the visible light spectrum. The WISE infrared telescope becomes like a magic set of glasses.
So just like a firefighter uses infrared goggles to look through smoke in a burning building to find people, astronomers can use infrared to see through dust clouds to look for forming stars in their cores.
But revealing these hidden heat signatures first requires an extreme deep freeze. WISE's 4 million pixel telescope can only photograph infrared images if the telescope is colder than the objects it searches for.
So we need to make sure that we're not blinded by the heat of our own telescope. On WISE, we use a tank of solid hydrogen that's frozen near absolute zero, and this keeps our telescope and our instrument cold. Just like a cooler full of ice, the frozen hydrogen on board WISE is eventually going to sublimate away. When we run out of all of the hydrogen ice, the telescope and the instrument will warm up to the point that we'll no longer be able to see.
Frozen to minus 447 degrees Fahrenheit, the hydrogen can only last for about 10 months. By that time, some 1.5 million photographs will create a giant composite picture of the heavens. A cosmic road atlas that can reveal new worlds for future space probes to target, potentially worlds with alien life forms. But if we are to find alien life many light years from Earth, we'll need a critical clue to lead us there. On Earth, that clue covers 71% of our planet: water.
One of the main reasons we're interested in finding liquid water is that we really would like to know, is there life elsewhere in the solar system? Life on Earth, as we know it, needs water to survive. It needs water to form. We hope to find life elsewhere, and a signpost for life might be first finding a place where there's water, liquid water.
Throughout human history, there was no proof that liquid water existed anywhere else in the universe besides Earth. Until a sophisticated space probe arrived on a mission of discovery to the planet Saturn in 1997. Cassini traveled 400 million miles and took 4 years to begin a multi-year spy mission to uncover the secrets of Saturn.
When the Cassini probe got to Saturn, not only did it study all the moons and the planet in particular, but then it went out of the plane, changed its orbit, and could look down on the rings.
One ring in particular attracted Cassini's scientists.
We knew that Saturn's outermost ring, the E ring, was made of very small micron-sized ice particles. Micron-sized ice particles don't last long in space. We knew there was a source of stuff in the Saturn system that was creating the E ring. We guessed it was Enceladus.
When Cassini approached the moon Enceladus, it witnessed a cosmic phenomenon and confirmed that water was indeed a key ingredient on another world.
The Cassini spacecraft has detected water under the surface of Enceladus. And the way it was detected was that these geysers are coming out from fissures in the cracked surface of Enceladus. And the water freezes as it comes out into the cold space surrounding Enceladus.
The constant stream of water ice particles feeds Saturn's E-ring, an icy reminder that if liquid water exists on remote planets in our own solar system, it might be found elsewhere in the universe. But Cassini's hunt for liquids wasn't over. It would have to use its sensitive instruments to penetrate other atmospheres of the Saturnian system.
The Cassini spacecraft has 12 science instruments. 4 of them are what we call optical remote sensing instruments. They see in the wavelength of band that humans see, or just outside of it. The spacecraft has filters that are designed to peer through that haze and see through to the surface below.
Cassini's instruments are designed to gather intelligence with different tools, much the same way that humans use our different senses. Cassini's direct and remote sensors first began studying Saturn's moon, Titan, a place that some believed could contain liquid water. Titan is bigger than the planet Mercury, with a dense atmosphere, thicker than even the Earth's atmosphere. In 1980, when the Voyager space probe flew by on its way to the outer solar system, its photographs hinted at another liquid phenomenon.
What the Voyager spacecraft told us is that that atmosphere is filled with hydrocarbons, methane, ethane, that create a thick photochemical haze. The Voyager spacecraft couldn't see through that haze.
When Cassini began studying Titan 25 years later, it also launched a satellite spy probe called Huygens. The probe penetrated the thick hydrocarbon atmosphere and landed on Titan's surface. What Cassini and its lander found was shocking.
Very early on, Cassini and Huygens had seen hints of the evidence of fluids on the surface of Titan. Eventually, they found hydrocarbons. They found hydrocarbon lakes, some larger than the Great Lakes. These are the first open bodies of fluids found in the solar system outside of Earth.
The lakes are filled by classic Earth-like rainstorms. But on Titan, the raindrops are not H2O, but slow-falling liquid methane.
A lot of the methane on Earth is in the gaseous state. It's called natural gas, in fact, and it comes from decaying organisms. And they're still decomposing, and they form this natural gas, which we can use as a fuel here on Earth.
Titan's liquid methane world could even harbor simple life forms, much like the single-celled life found in the depths of Earth's oceans.
So there's a lot of excitement about the possibilities that could be out there. Planetary systems out there are active, interesting, and very varied, and we know that life can take many different forms.
Life might be found on distant planets orbiting other stars. The problem is getting there. But a new super engine with a propulsion system similar to microwave oven technology is preparing to turbocharge deep space travel. Space probes can boldly go where no human has gone before. But for decades, scientists have wrestled with a harsh reality. Space probes can fail. Every one that succeeds is built upon a half-century of failed missions and shattered dreams. The history begins in the 1960s, with NASA's first attempts to reach Earth's nearest neighbors.
Our first Ranger probes were designed to take images of the moon en route to smashing into the moon, and our first 6 Rangers missed the moon entirely. But we learned quickly, and a few months after the Ranger probes, we sent a successful spacecraft to fly past Venus.
In 1962, the American probe Mariner 2 is the first spacecraft to fly past Venus. It reports that our nearest neighbor is no place like home.
We used to think that Venus might be like a twin sister of Earth, with hot, steamy jungles. Well, the space probes taught us that, sorry, Venus isn't like that.
The NASA probe proves that Venus is too hot and its pressure is too great to support any life. But in 1970, the first probe to land on the planet isn't American, but Soviet.
The Venera probes had an inner shell, an inner hull of titanium that was tough. It could withstand, at least for a while, the crushing pressure and the intense heat of the Venus surface.
So the early probes to Venus got destroyed in just half an hour or under an hour. They were able to take data for only a short amount of time before they got crushed.
But the data sent back before Venera's destruction is precise and surprising.
Conditions on the surface of Venus are hellish. The temperature is about 860 degrees Fahrenheit. That's really, really high. I mean, the boiling point of water is 212 degrees, and lead melts at a temperature slightly lower than 860. So you'd have molten lead on the surface of Venus if you had lead there. It's a really bad place to be.
Venus is an extreme training ground for probe scientists. But there is a more distant and difficult goal: one whose extremes are even more destructive than Venus, the outer planets. And getting there requires more than just a big rocket.
One of the biggest problems with space probes is having enough fuel to get where you're going. You do a rocket burn, you burn a lot of fuel, and if you keep doing a bunch of rocket burns, you're going to run out of fuel and then your probe is dead.
But there is a solution built into the fabric of the cosmos: gravity.
In the early 60s, it was discovered that we can use the gravity of the planets to assist a spacecraft to speed it up, to fling it further out the solar system. That opened up the outer solar system to exploration.
The technique is called gravity assist, a virtual engine that harnesses the immense gravity of planetary bodies to assist a spacecraft on a planned trajectory.
Hitting a baseball is a lot like a gravitational assist. The space probe comes into a planet, it gets caught by the gravity and redirected in another direction, just like hitting a baseball with a bat, and it directs the baseball in another direction.
When the bat collides with the baseball, it changes the baseball's direction of motion, and it can propel that baseball with a much greater speed than what it originally had.
By harnessing the gravitational pull of planets, NASA has been able to hit probes out of the park and to the outer planets. Cassini's home run journey covered 170 million miles to the methane lakes of Saturn's moon, Titan.
Without those gravity assists, this spacecraft, which weighs 12 tons in Earth's gravity, never would have made it to the outer solar system. We don't have a booster big enough to send it to Saturn directly. We would not have explored Saturn were it not for the gravity of the inner planets.
Now, 21st century space exploration is poised to send probes beyond the outer planets, to distant stars. But gravity assist doesn't have the power to get us there. Traveling into deep space requires propulsion that seems to come straight out of science fiction: the ion drive.
Ion engines are like a mini linear accelerator. You accelerate ions out the back, the spacecraft goes in the opposite direction. That ion engine has very, very low thrust, but it operates for months at a time and eventually gets the spacecraft up to faster and faster speeds.
The ion engine replaces the chemical fuel with an inert gas like xenon. The xenon is given an electrical charge, or ionized. An electrical field then accelerates the ions out the back of the spacecraft, propelling it forward. Ion propulsion is not like most rocket engines. A standard chemical rocket engine propels itself like a double-barreled 12-gauge shotgun.
This shotgun is actually a chemical rocket engine, just like the Space Shuttle main engines. I'm sitting on Earth on a dolly track. So the question is there enough thrust from the shotgun to overcome the friction between the wheels and the track?
A single blast moves the dolly about 6 inches. A second blast keeps the momentum going. But now replace the big double-barrel shotgun with a smaller weapon.
Now I have a .22 rifle. It's a little different than the shotgun. The shotgun shot many pellets out at a fairly moderate velocity. The rifle shoots a small pellet out at very high velocity. Now the difference is that this is more like an ion engine.
The .22 recoil moves the dolly less than an inch. Multiple shots move it slightly more.
But if we were in space, the .22 would be just like the ion engine. It would start pushing us slowly and eventually build up until we reached a really high velocity.
By compounding tiny thrusts through the vast frictionless depths of space, the ion engine can propel a probe for years. The technology could mean the end for massive rocket boosters in space probe travel.
Chemical fuels are a problem because they're pretty inefficient. They weigh a lot, they have a lot of mass, and you have to transport all that stuff out there. And that means the rockets that launch the spacecraft have to be even more powerful, even more expensive.
Lightweight ion engines have already passed the test in outer space. They powered the Deep Space One probe in the late 1990s and recently propelled the probe Hayabusa of the Japanese Aerospace Exploration Agency and helped it land on an asteroid.
Ion engines will completely change deep space exploration because we can go a lot more places without having to carry a lot of fuel. And we can get there in the end faster depending on where it is we're going.
One of the places we may be going is our planetary neighbor. Currently, the European Space Agency's Mars Express probe holds the Earth to Mars speed title at 6 months. But one advanced ion engine is expected to shatter that record.
An ion engine could cut the travel time to Mars down to just a mere few weeks.
5 weeks to Mars is only the beginning. The next step in ion drives will amp up its speed as much as 100 times faster. It's called VASIMR, an acronym for Variable Specific Impulse Magnetoplasma Rocket. VASIMR's ion engine gets an added radio frequency generator and a second stage.
One of the key things is it works kind of like a microwave oven. Just like a microwave beams electromagnetic energy into the food to superheat it. As the plasma gets superheated, then it's got way more energy. It's got these really strong magnetic field that takes that superheated plasma and shoots it out the back end at really high velocities.
The ions can be superheated to about 1 million degrees. That's enough to send a probe far beyond our solar system. As rocket technology advances, the gates of deep space are swinging open to exploration. All we need is a destination. One space probe is right now scanning the heavens for that destination. A new Earth, and possibly a new form of life. Space probes are on the cutting edge of one of astronomy's oldest quests. The search for another Earth. Now, a new generation of robotic explorers seeks evidence of extrasolar planets. And we're finding them.
An extrasolar planet is simply a planet that orbits another star. We have 8 major planets orbiting our sun, and our sun is a typical star. And so a question that has loomed for centuries is whether there are planets that orbit the stars that we see at night.
Since the days of Galileo, scientists have believed there must be other planets among the billions of stars in the sky. But the quest for extrasolar or exoplanets wasn't successful until 400 years after Galileo. In 1995, in the Pegasus constellation just 50 light years from Earth, scientists discovered the first true extrasolar planet, 51 Pegasi b. It was found only through indirect clues.
We were only being able to find these extrasolar planets using a technique called star wobble. If you have a big planet like a Jupiter out there, it would cause the star's motion to wobble. But we couldn't really sort of directly tell it was there.
Also called the Doppler effect, the wobble is observed through a telescope. If the star's light regularly shifts toward red or blue wavelengths, and then back again, then an orbiting planet must be causing the light to shift.
In the last decade or so, astronomers have been extremely lucky to find hundreds of planets around other stars. But the planets we've been finding are the large ones, the Jupiters, the Saturns, some Neptunes. We have not been able to find the Earth-like planets, if they're out there.
There are now hundreds of verified extrasolar planets. But are any of these planets close enough for mankind to explore? That's what Annabelle C. from Erie, Pennsylvania wanted to ask the universe when she texted us. How long would it take for a space probe to reach the nearest exoplanet using the best propulsion available today?
Annabelle, that's a really interesting question. And in fact, there's no set answer. Using today's technology, a space probe could reach another star in about 100,000 years. The nearest known exoplanet is about 10.5 light years away, but there might be a more nearby one. Or we might improve space propulsion technology in the near future. So maybe we could get that down to about 10,000 years in the relatively near future. But something like 50 to 200,000 years is a good answer for right now.
Finding the Earth-like planets means looking deeper into the cosmos at dimmer and more distant stars. A revolutionary method of watching these dim stars could soon pinpoint the first new Earth. It's called the transit technique, and it offers a dead giveaway that an orbiting planet is crossing between the star and our viewpoint from Earth.
So let's imagine this reflector is like the face of a star, and a bug flying in front of that reflector is like the planet. As the bug goes in front of and around this reflector, it will block a little bit of the light from the reflector, just as would happen when a planet crosses in front of a sun-like star.
The amount of dimming is often less than 0.1% of the star's light output. Barely noticeable, but it's more than enough for one far-sighted space probe that's now scouting the cosmos.
We'd love to know if there's another Earth-like planet out there somewhere, and the Kepler mission has a good chance of being able to see it if there is one.
The Kepler space probe is the powerful eye scientists will use to find the Earth-like planets. The proverbial needles in the haystack. The probe's telescope is using a 95-megapixel camera to watch for the transiting planets.
The Kepler mission is using the so-called transit technique to search for new extrasolar planets. With the transit technique, Kepler is watching thousands of stars, waiting for their light to slightly dim when a planet passes in front of the star.
The Milky Way is composed of billions of stars and potentially billions of Earth-like planets. The odds of finding one Earth orbiting one particular star are very low. So Kepler will train its unblinking eye on many thousands of stars at the same time.
Here I have a DVD to represent a planetary system with the star in the center and a planet going around the outside. And of course, most of the time, the planetary system is tilted to our line of sight. And so as the planet goes around, it never crosses in front of the star, blocking the starlight. But if we're lucky, and the orbital plane of the planet is seen edge-on, then the planet crosses in front of the star, blocking some of the starlight and dimming the star. And so you have to be watching tens or even hundreds of thousands of stars to be lucky enough to catch a few planets that happen to cross right in front of the star.
As the world waits, Kepler watches the distant stars moment by moment. But if it does find a new Earth, what can we actually find out about it? What will it look like? Could there be life?
Once Kepler finds Earth-like planets, and I'm fairly sure it will be successful, the next thing will be to try to analyze the light from that planet. What's the chemical composition of this Earth? Does it have an oxygen atmosphere, or is it just carbon dioxide or methane? Does the planet have continents and oceans, water on the surface?
Currently, we don't have the technology to analyze the atmosphere of a distant Earth-like planet. But that's about to change. In 2015, the James Webb Space Telescope will offer 4 times the imaging capability of the Hubble Space Telescope. Secrets of the space probes. At this very moment, millions of miles from the Earth, human beings are sampling, measuring, photographing, and even sniffing the dust and gases of other worlds. But not in person.
The environment of space is very hostile to people. It's got a
Beginning, there was darkness, and then bang, giving birth to an endless expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. They are humanity's eyes and ears in deep space, exploring the plains of Mars, the geysers of Saturn's moon, and the blazing surfaces of distant stars. They are space probes, robotic explorers that are now humanity's interstellar avatars.
They can go places and see things that we could never.
While others, like Deep Impact in 2005, are ordered on kamikaze missions to smash satellite probes into comets. Others are sent to uncover the secrets of planets like Mars, Jupiter, Saturn, or their moons, imaging and analyzing them from orbit and landing on their surfaces to explore or dig for samples.
Our probes are used to answer fundamental questions about planetary composition, atmospheric composition, geologic atmospheric processes, how are planets both similar to and different than Earth, and the big picture question, is there life?
Ever do from here on Earth.
Space probes fan out across the solar system, returning data that change everything we thought we knew.
If we could find indigenous life elsewhere in our galaxy, it would be one of the greatest discoveries in the history of humans.
Probes collide head-on into icy comets, photograph the edge of the universe itself, even seek planets in other solar systems.
We're at a golden age in the search and discovery of Earth-like planets.
A new generation of robotic explorers is redefining the galaxy itself by unlocking
Extremes of temperature, extremes of vacuum, high radiation fields, all kinds of things that are really inhospitable to human life.
Our eyes and ears are robotic proxies sent on missions to discover the secrets of our solar system and beyond. They are space probes, and they were built to survive the hostile atmospheres and perilous worlds that mankind cannot.
Our space missions are able to survive these difficult environments, and they can go places and do things that we could never dream of without them.
Some probes, like the Hubble Space Telescope, float comfortably in Earth's orbit,